Hey everyone, thank you for coming. So my name is Shrishti Dasarati, and I'm a third-year biological oceanography PhD student at Scripps Institution of Oceanography. And I'm here because I thought that this forum really gave me the chance to talk about my PhD work, which is incredibly interdisciplinary. And I'm going to be presenting on the multi-year seasonal trends between sea ice, chlorophyll concentration, and clean marine aerosol optical depth in the Bellingshausen Sea. So to jump right into my study area, so this is a schematic of the Bellingshausen Sea, which is on the western side of the Antarctic Peninsula. As first and foremost a biological oceanographer, I'm interested in this region because it's an incredibly productive environment with massive phytoplankton blooms every Antarctic spring and summer. And this fosters an incredibly rich tapestry of life that's intimately tied to the physical environment. Not just that, but as a polar environment, it's particularly difficult to study. And despite considerable effort that's taken place, not much is known about a full-scale ecosystem analysis of this region. And this gave me a really great opportunity to use satellite data to really understand this ecosystem and this environment from a variety of different perspectives. So this figure here explains a lot of what I'm studying, and the image is from a paper by Gabrick et al. In 2018, and really emphasizes some of the seasonal trends that I'm interested in. To give a bit of a background to my region, I thought it helps to first walk through some interesting processes that occur. First, as Antarctic spring and summer approach, sea ice melt occurs. This melt, which occurs alongside an increase in sunlight availability and nutrients, fosters a huge phytoplankton bloom in this region. Phytoplankton, in turn, produce a class of aerosols known as marine biogenic aerosols, or MBA, and affect the lower atmosphere of the polar environment. Not just that, but the increase in open ocean from sea ice melt also increases inorganic aerosols such as sea salt or sea spray aerosols from wind over the surface ocean. Because of this, the dynamics are interlinked and diverse in nature. Spring and summer occur alongside sea ice melt. Phytoplankton blooms because of this melt of sea ice, as well as increased sunlight availability and nutrient availability. This in turn fosters the formation of biogenic aerosol. So my hypothesis is that marine aerosol formation is tied to seasonal sea ice melt and increased primary productivity in the Bellingshausen Sea of the Western Antarctic Peninsula. And this hypothesis has two parts. In relation to sea ice, my hypothesis is that an increase in aerosol presence is temporally linked with the seasonal decrease in melt of sea ice. In relation to ocean color, or chlorophyll A, my hypothesis is that marine aerosol formation will increase during the onset of the seasonal phytoplankton bloom period in the Bellingshausen Sea. And this analysis was mostly undertaken this summer, and I should mention the work is getting really close to completion, so I'm really excited to share what I have so far. To talk more about the phytoplankton bloom that occurs in this region, I thought it would be helpful to have these seasonal climatologies, where all 4 seasons from every year, 2006 to the end of 2018, are condensed. And to orient you to this figure, notice the arm of the Western Antarctic Peninsula. As you can see, the phytoplankton bloom kicks off in spring across the region along the coastline and is extremely high in the summertime. I'm sorry for the formatting here because I know it's probably a little bit difficult to read, and I'm using this figure principally for background right now. But if you look at the color bar between spring and summer, the intensity of the summertime color bar is actually 3 times that of the one that occurs in the springtime. So the summer phytoplankton bloom is really immense and also occurs all across this region. And this phytoplankton bloom also persists into the fall. And these ocean color seasonal trends really highlight the biological productivity of this region. Similarly, in regards to sea ice, there are seasonal dynamics that you can visualize. Interestingly, sea ice in fact freezes from winter to spring, as indicated within the red circle, which is here. But then melt really kicks into gear in the summer months and hits the lowest extent in the fall. And maybe you can now start visualizing how this might be tied into the prior ocean color seasonal dynamics as well. At the end of the day, none of this research would be possible without a whole suite of NASA Earth observing satellites. I'm not going to talk about this in too much detail, But to give a little bit of a background into my methods, the satellite that I used for my analysis of aerosols and ice was the Cloud Aerosol LiDAR and Infrared Pathfinder Satellite Observation, or CALYPSO. And the main satellite for my analysis of ocean color, which most of you are probably familiar with, is MODIS Aqua, as well as the AMSR-E instrument that was used to get wind speed data. CALYPSO and MODIS also used to fly in formation one after the other, which provides greater correspondence between the data sets that I'm using. And one interesting quote that I found from the NASA Gov website was that the instruments on these satellites are used synergistically to improve our understanding of clouds, aerosols, atmospheric chemistry, and other elements of the Earth environment and changing climate. So to talk more about my methods, particularly for aerosol analysis, I thought I'd show this schematic of one swath over the western Antarctic Peninsula by CALYPSO. CALYPSO provides a curtain of data. So on the y-axis is altitude, going up to 12 kilometers. So here, indicated by the red arrow, for example, is a slice through clouds. But what I'm interested in are low-lying aerosols over the ocean, here. The top figure shows backscatter, and after that, an algorithm is applied by CALYPSO that distinguishes clouds from aerosols. After that, CALYPSO also has the capability to subtype my aerosol and pulled the clean marine aerosol subtype, which was used in my analysis, and is indicated by the dark blue region in the lowest figure, which is here. I developed a method of calculating optical depth, which is a value that is related to the amount of aerosol in a column of air, and integrated the clean marine aerosol extinction coefficients across a chosen altitude range, which most often captured the aerosol signal. Last, all of these metrics were quality screened, and only the clean marine aerosol subtype was chosen for my analysis. Using clean marine optical depth, which is a mouthful, so I'm going to just call it CMOD, I developed seasonal climatologies similar to what I showed you earlier. Again, in relation to this, my hypothesis was that marine aerosol formation is tied to seasonal sea ice melt and increased productivity. So here I've made climatologies, and the bin size is 1 degree latitude and 2 degrees longitude to capture as much information as I could. Again, we have the Antarctic Peninsula, and what's interesting is that despite noise, there's a seasonal increase of CMOD from winter to spring and to summer, which begins to decrease into fall and into winter again. And now here I'm presenting my seasonal climatologies of ocean color, presented a little bit differently. I've adjusted the resolution so that it's the same as the earlier CMOD seasonal climatologies. And it shows, as described earlier, phytoplankton blooms that occur starting in the spring, which increase quite a bit in the summer and persist to a lesser extent in the fall. And one of the other things that I was interested in is whether the increase in my CMOD variable, or aerosol amount, could be explained solely by an increase in wind speed, which might loft up sea spray or sea salt aerosol. However, what's interesting is that wind speed is lowest in the summer. Perhaps this could be an indication of the role of ice melt and biological productivity that influences my clean marine aerosol optical depth, instead of solely being explained by an increase in wind speeds. After that, a concurrent goal for me was to develop these time series of all of my variables. And this figure is a lot, but I'm going to walk through it and zoom in, so don't worry. So here we have a monthly average time series from 2006 to 2018 of the entire study area. And the black line indicates CMOD, or aerosol amount again. The blue line indicates ice, and the green line indicates chlorophyll A. And what's really interesting is that it did show the same trends year after year. So to visualize this better, I'm going to zoom in on a few years, which are represented by the red box. And here's now a zoomed-in view to look more closely at these trends. So the black arrow again indicates CMOD. And what's interesting year after year is that the increase in CMOD occurred at the onset of the Southern Hemisphere summer. Next, we have the blue line, which indicates ice. And again, year after year, the increase in CMOD occurs annually with the melt of ice. The green line indicates chlorophyll A. And again, in relation to CMOD, the increase in CMOD occurs alongside or even slightly before the increase in chlorophyll. After that, I also developed time series of my wind speed and my CMOD variable alongside each other, where black again indicates CMOD, and my blue indicates wind speed. And what's interesting is that, again, this is a monthly average, and there's a little correspondence between CMOD and wind. So because of this, the CMOD signal is likely more indicative of a biogenic aerosol signal than one of increased wind speed causing an increase in sea spray or sea salt aerosol in the lower atmosphere. So what were my final conclusions? So a lot of work went into this, and what I did was I developed seasonal climatologies and time series of sea ice, chlorophyll A, and clean marine optical depth. And this was from a variety of different instruments on MODIS and Calypso. And my final conclusions are that seasonality is detected and CMOD increases in late spring until early fall, synchronous with a decrease in sea ice concentration and increase in chlorophyll A concentration. There is noise present, however, in my CMOD variable, and this is likely attributed to attenuation of the Calypso LiDAR signal and possible presence of clouds at low altitudes. However, these trends do support our hypothesis that increases in the production of biogenically derived marine aerosol occur seasonally during Antarctic spring and last until early fall. After that, so this is really the first phase of my PhD, and my next steps are to statistically verify trends between these different variables. So with that, I have a lot of acknowledgements and people who've helped me along the way. So none of this work would be possible without my lab at SIO, as well as my advisor, Dr. Jeff Bowman, and the NASA Calypso team, which really helped me develop this project, as well as the NASA summer program, which helped me go out there. And again, I'd like to thank the Esri Ocean and Atmospheric GIS Forum for having me. So thank you.